talked about things being deterministic versus things being probabilistic, right? So macro scale, we can project the trajectories of different things and know exactly where they're going to land. Our brains are actually really good at doing that on the fly without math, right? If you throw something, you know about where it's going to land, and if you're a professional basketball player, you know pretty much exactly where it's going to land if you're shooting baskets. And inside of an atom, though, when we're looking at the locations of electrons, it's all probabilistic. And they're determined by this Schrodinger's equation and these wave functions. And this is psi, which is psi, psi squared. So a plot of psi squared tells you the orbital, represents the orbital, represents the area where you're most likely to find the electron. So electrons are not like hazy clouds. They just are likely to exist inside of what looks like a hazy cloud. So they're somewhere in there. But we can't determine the exact location at the same time as everything else. So the thing that you need for tonight is basically the descriptors that we use for describing the shapes and locations of orbitals around an electron, or around an atom, around a nucleus. And these are the quantum numbers that you're going to need. Some of them they'll be kind of familiar. They should be familiar once we start tying them to the sort of Chem 20 names that we've used for things. N is your principal quantum number. Also for the periodic table and electron configurations corresponds to the row, right? So this is n equals 1, n equals 2, n equals 3, n equals 4. The angular momentum quantum number is going to be the type of orbital. So that's your S, P, D, and F. I'll write that here. But they'll be represented instead by a number, and that'll be L equals 0, 1, 2, 3. So 0 is S, 1 is P, 2 is D, 3 is F. And then you have a magnetic quantum number, which corresponds to each of the different types of orbitals. And there are, what is it? L times 2 plus 1. I think it's actually like on one of the next slides. So the magnetic quantum number corresponds to the specific orbital. So if you remember, the s orbital only has the sphere. P has 3 different dumbbells. D has the like double dumbbell shapes and then the donut, or the dumbbell with a donut around it. And F has 7 different orbitals. And we'll get to that in the next slide. The spin quantum number only corresponds to upspin or downspin of each electron. And that actually only has 2 values. It could be -1/2, which is down, or it could be +1/2, which is up. We'll see these all again. And actually, for Monday's lab, these correspond as well. The quantum number n is what you need to use, if you haven't done all the math already, is what you need to use to correspond those energy levels with the energy changes that you observe from the emitted wavelengths of light. So increasing n, you get higher or farther and farther away from the nucleus, means you have higher and higher energy. It's not linear, so the closer you are to the nucleus, the closer an electron is to the nucleus, the more stable it is. And it's being stabilized by that, by the interaction with the nucleus. So anything that's really close to the nucleus in something like n equals 1 is going to be especially stable. Once you make a jump away from that, it gets less stable. And then the differences between every subsequent energy level gets smaller and smaller because there's less stability. And so this is what that looks like, right? This first jump is really big. This next jump is much smaller. And then each jump after that will be a little bit smaller, but they'll probably be much closer to the same size. Okay, so the angular momentum quantum number, that's L, which when I write L's, because it's like supposed to be L in italics, we'll do a cursive L. Those correspond again to S, P, D, and F, and you just remember to start at 0. So L equals 0 is S. And so this is always going to be n minus 1. So if you start at n equals 1 on the periodic table, that's the first row. The only orbital we have is S. You go to the second row, right, so that's 2. So n is 2, so 2 minus 1 means that you have 0 and 1, which is S and P. So you kind of use the periodic table as a guide on those. So if n equals 3, what values of L are possible? Yeah. So it'll be C, because we can have up to n minus 1. So it'll be 0, 1, and 2. It means that we have S, P, and D. So that would be here. And we do have 3D orbitals. They're just not filled at all by the time we get here. The magnetic quantum number, if you can do, so I think n is pretty easy, right? That's just like the row of the periodic table. Start with n. Figure out how many levels of L. Remember L minus 1, or n minus 1. That's the highest one you can have. For M sub L, the magnetic quantum number, I think is the easiest, because it's whatever L is. And you just do from negative L to positive L. So what does that mean? It's all the integers. So if L equals 2, then you can have negative 2, 1, 0, positive 1, positive 2. If L equals 3, then what would my possible M sub L be? Negative 3, negative 2, negative 1, 0, 1, 2, 3. So these are all the possible M sub L's. Okay. So what values of M sub L are possible for L equals 2? Negative 2, negative 1, 0, 1, 2. So if you can get to L, M sub L, you just go from negative to positive, all the integers. And the quantum spin number is pretty easy also. So M sub S can either be positive 1/2, negative 1/2. And so in any given orbital, you can only have 2 electrons. One of them can be positive 1/2, the other one can be negative 1/2. Yeah. So it's the spin of an electron. M sub S. So you can kind of think of all of these numbers. Like if you think about electron configurations, they're kind of an address for the electron. And so for any valence electron, you could sort of say that it's in the 1s2, 2s2, 2p6, that kind of thing. This is a more specific and probably more quantitative description of where that electron is going to be. So number of sublevels within a level n. So n equals 3, there's 3 sublevels in that level. If n equals 2, there's only 2. If n equals 1, there's only 1. If we go to n equals 4, that's where you add in the f orbitals. There's 4 sublevels. So whatever n is tells you how many sublevels there are. The number of orbitals within a sublevel is 2 times L plus 1. So, right, so if we're L equals 1, so 2 times 1 plus 1, that equals 3. And that's -1, 0, +1, that's 3. So there's always going to be, right, the same number of orbitals on either side of 0, and then the +1 is 0. So we take the number, multiply by 2, add 1. And then the number of orbitals, the total number of orbitals in a level, so if we want all of the orbitals in n equals 3 is just n squared. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 squared is 9. I made the same face when I read this earlier today. It feels like a weird thing, but so n equals 2, right? How many orbitals should there be, regardless of sublevel? How many orbitals? What's n squared? 4. And so in n equals 2, there's the 1 2s orbital, and then there's 3 2p orbitals. So for a total of 4 orbitals. Yeah, just like the orbitals in Chem 20. So these are different descriptors for those same orbitals, essentially. Parameters of the Schrodinger equation. All right, so list all of the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? I'm like not super happy with the way this is worded. I think what they're asking for though is not for everything up to 5D, but everything in 5D. Well, I think there's 2 questions here. So for 5D, right? So we've got N, we've got L, we've got M sub L, and we've got M sub S. Those are the 4 quantum numbers. So what is N? And what's L? Those are, oh no, that's M sub L, M sub L. So this is, I would suggest on the exam, immediately write down 0, S, 1, P, 2, D, 3, F, just somewhere, so you have that as a reference. Right, so okay, D, these are the L's. So what L is D? That's a confusing question. So the angular momentum, is that the angular momentum quantum number? I always forget these names. Yeah, angular momentum quantum number is L. So yeah, L here would be 2. Because L equals 2 is the D. So then how many M sub L quantum numbers do we have? 5 total, yeah. And they'll be -2, -1, 0, 1, 2. These should probably be +1. And then what would our M sub S? There's only 2 possible. Yeah. plus 1/2, and minus 1/2. And then we would have those for, there'd be a positive 1/2 and a negative 1/2 for -2, -1, right? So we could essentially say these, if we wanted to count like the total number of possible quantum numbers, be that times 5. There'd be 10 of those. I don't think that's necessary. So for the how many 5D orbitals exist, again, I don't like the way that this is worded. Yeah, I just don't like the way this is worded. Because you could take this, I think the most straightforward way is, right, how many m sub L levels are there, essentially? Because each of those corresponds to a separate orbital. So how many levels m sub L do we have? 5. And not because it's 5D. How many total orbitals should there be in the n equals 5 sublevel for principal quantum number? 25. So like the total orbitals would be n squared. So 5 squared would be 25. So it'd be 1, 4, 5. Yeah, I guess the F exists, but it's not filled. So we'd have 1, 3, and then 1, 2, 3, 4, 5, 6, 7. So 4, 9, 7, 13. That's 20. Because there's S, P, D, F. No, that's 9, not 20. Sorry, 9. 16. Yeah. So 25 suggests that there are other orbitals beyond F. I actually think there are, but unless you're getting up into crazy excited energy states, they're not going to exist. Okay, one last one, and then that really does kind of cover it for everything that tonight's lab is about, looking at the actual shapes of these orbitals. And we've got the computer cart here. If you brought your own laptop, probably want to use your own laptop. Or I think it should probably work on an iPad too. Give it a try on your iPad first. But last question here. Each set of quantum numbers is supposed to specify an orbital. However, each set contains one quantum number that is not allowed. Replace the quantum number that is not allowed with the one that is allowed. Let's focus on A then. I think there's one quantum number that's always allowed. At the N kind of sets what everything else should be. So here we have N equals 3. So which levels of L should be allowed? Yeah, so zeros, 1, 2, or 1 and 2. So there's 3. So this is the one that should not be allowed. What should it be instead? What about in B? Yeah, so if we have 2, that means we can have 0 and 1, so that's fine. And this one's fine. But if we have L equals 1, that means we can have -1, 0, and +1. So what's a possible number that this could be? Yeah. Here you could really pick, it could be -1, it could be 0, it could be +1. All three of those would be allowed. And then for C, yeah. 0, and then epsilon L equals 0 is allowed. Okay.